Professor, thank you for your introduction, and thank you for everyone for coming. Okay, so today my topic is about forward and inverse approximation theory for. Is this the pointer?
You should use the keyboard.
Okay.
Because it's a laser pointer, yes.
Okay. Okay. Or for linear temporal convolutional networks. Okay. Okay, so basically, what we are considering have three parts. First is about sequence modeling, and next is the approximation theory in the sequence modeling, and also what about the approximation property of a specific sequence modeling architecture. And in fact, we have a series of works considering different architectures, the approximation property of different sequence modeling architectures. And instead of going very details about the specific setting, I'm going to introduce the overall settings and the general idea of our works. Okay, so about the sequence modeling problems, what we consider the sequence. So for sequence modeling, we are considering the input and output are sequences, and what we do here is that we regard the sequence as a function of time t. So both the input and output are sequence of time t. The time t belongs to an index set I. So here the index set may be real numbers or integers, depending on we are considering continuous settings or discrete settings. Okay, and now we have the input and output. We are going to define the sequence to sequence relationships. And let's just consider the sequence at the specific time t. So let's say at the time t, the output yt, it possibly depends on the whole input, the entire input sequence x. So it's naturally to define it as a functional. So here htx, the ht here is a functional, and in order to consider the sequence to sequence relationship for the entire time index, we just need to consider a sequence of functionals here. So this is our definition of the sequence to sequence relationships. And here I'm just going to give an example here. So a very simple sequence to sequence relationship is just a convolution. So what we have is when we have input sequence x, and we are going we're going to consider the convolution with a Gaussian kernel, and on the left-hand side is the input sequence. So it's just a function of time t, and on the right-hand side is also a function of time t. So what this sequence to sequence relationship do is that if we have a noisy input, and this target will smooth it, and we have a smooth version of the output. So this is basically what our sightings about the sequence to sequence relationships. And okay, and next, I will introduce the approximation series we are considering. Okay, so basically we are considering three different questions in the approximation series here. So the first is universal approximation, which we call density type result. And we also have the forward approximation and the inverse approximation. So for the forward approximation, we call it the Jackson type approximation rate. And for the inverse approximation, we call it the Bernstein approximation rate. So why we call this name here is that this name actually comes from the classic polynomial approximations. And next, I will, using the polynomial approximation as an example, and introduce some of the terminologies here. So we write the target space at C. So for the polynomial approximation, we are considering just the continuous functions defined on 0 to 1. And so the target space means that all the functions we want to approximate, so it's just our targets. And next is the hypothesis space, we write it as H. So what is hypothesis space is that it considers some simpler functions. It's usually a small subspace of the target space, and it has some simpler functions that can easy to be represented. And we want to use these kind of simple functions to approximate the functions in the target space. So for this particular example, we are using the mth order polynomials to try to approximate the continuous functions defined on 0 to 1. And so for the first one, the density result is just saying that we are considering whether the hypothesis space is dense in the target space. This one is particularly important, is that because we are using a smaller space to approximate the target space, we want to ensure that this space is large enough. So the Stone-Weierstrass theorem states that for any continuous function, there exists a polynomial that can approximate it to arbitrary accuracy. So this one is just to say that for any target in this one, for any target we are considering, we can find a polynomial in a hypothesis space to approximate. And next, even though we have the density result here, we do not know the approximation quality of this one. For example, give two different targets. How do we know which one is easy to be approximated and which one is difficult to be approximated? So this comes to the forward. We need to consider the forward approximation, which is the Jackson theorem. It states that for any alpha time continuously differentiable function in the target space, the Bayes approximation is bounded by this rate here. So the C alpha here is a constant just dependent on the alpha, and CH here is we call it a complexity measure of the target in the target space. So what this rate can tell us is that for the target for any target in the target space, we can compute this complexity measure, and actually, in fact, this one is a sovereign norm of the target. And when we have this rate and given a target, we know how the error behaves when we increase the number of parameters or we increase the number of terms in the polynomial. So this one gives a characterization of the target space, such that we know a target in this one is easy to be approximated if and only if this norm is small and its smoothness alpha here. And when we have this and we need to know that this one is just an upper bound. It's just an upper bound, and we are wondering. And when we ask, can the error be decreased faster than this one, or is this bound tight? And here to answer this question, we need to consider the inverse approximation here. And the Bernstein theorem says that if the error bound, when we increase the m here, the error follows this one, then the target must be alpha time continuously differentiable. So what it means that if the error decays faster than this one, then it must be smoother. So alpha time continuously differentiable function the error bound cannot be decreased faster than m to the alpha times. Okay, so this is basically the general idea of the approximation of the approximation theory here, and we want to apply this one to machine learning and sequence modelings, and we want to see how the different sequence modeling architectures have this kind of rates here. Okay, so in this work, we are particularly considering linear temporal CNNs here. And for the target space, so we consider target as continuous, linear, causal, and time homogeneous functionals. And this is just some conditions on the functionals. And after some derivations, we can prove that all the functionals satisfying these conditions have this unique form of representation. So each functional can be represented in this form. And this row here is unique. So what this theorem said here is that for all the target, it is related with the function row here. And this row is we call it a representation of the target. And next, for the hypothesis space, we define the linear temporal CNN as this one. So it's a convolution with a filter row height here, and the row height is a M channel and K layer CNNs here. So we can write the whole filter in this form. So what this form is that the M here is the number of channels, and And the convolution here is we have k dilated convolutions, and it corresponds to the k layers of the CNNs here. And we can observe that these two have a similar form. So instead of just considering the approximation between the two sequence of functionals, we reduce to consider the approximation of functions here. And next, here is an illustration of this modeling architecture. So this is actually inspired from the WaveNet architecture. So it's a dilated CNN. So we know that the CNN, the most important characteristic is that it have a finite filter length. So let's look at this picture. We have a filter length of 16 here, I believe. Yeah, 16 filter, and build up to each layer we use dilated convolutions. So actually this filter have length 16, but it's only built up with 8 number of parameters. So the idea here is that we want the dilated convolution tries to build a large filter with few number of parameters. And in this way, we can save number of parameters in the model. And of course, because we are using fewer parameters, the target must have some properties, and must have some special properties here to let the model to have good approximation here. Because definitely we cannot use it to represent arbitrary filters here. And okay, so in order to analyze this problem, we propose a tensorization process here. So recall that we have we can convert a linear filter into a tensor here. So what we do here is that, okay, let me go back. So recall that this is the definition of the convolution filter, and we prove that this convolution is related with this tensorization through this equation, such that if we just replace the dilated convolution to the tensor product here, then this actually results into a special type of tensor here. And now we also tensorize the target representation rho here. And what we have is that we just need to consider the approximation of two tensors here. So, okay, so this is the approximation error of the target and the model. It is bounded by this equation here. So the first part is the error of the two tensors. So recall that the CNN filter is of finite length. So and the target may have infinite length. So we have two parts of error. The first part is considering the finite length within the range of the CNN filter, and the second part is the part the CNN filter cannot cover. So it's totally depend on the behavior of the target. Okay, so based on these two part of errors, we define two complexity measures here. And what the complexity measure tries to do is that just recall that what we do in the polynomial approximation. We try to give these two complexity measure so that we can have some approximation rate on this architecture. So the first one is for this part, and this sigma here is the singular values of this tensor through the higher order singular value decomposition here, and the g and f. The g here is a decreasing function, so this g is fixed. It is used to measure the decay speed of the singular values here. Obviously, measuring the spectrum, the decay of the spectrum here of the target. And for this one, and for the second complexity measure, we consider the decay of the tail of the target. And the f here is also a decreasing function. It is used to measure the decreasing speed of the tail of the target. And based on these two complexity measures, we have our main results here. So on the first one is the forward approximation, which is a Jackson type result. It says that for any target in the hypothesis space, we have the space approximation error bounded by this rate here. So this G and F, recall, is two decreasing functions, so that when the number of channels and the number of layers goes to infinity, this will convert to 0. And the two complex measures defines the decreasing speed of this error bound. And by given this, we want to ask, is this error bound tight or not? So that, or we want to say, will the error decay faster than this bound? And the Bernstein type result, or the inverse approximation result, says that this is indeed tight. So let's look at the proposition here. So suppose for any number of channels and the number of layers, if the target can be approximated according to this bound here, then we must have the complex measure of the target is less than A and less than B here. So this says that if the target can be approximated by this rate, then its complex measures cannot be larger than this one. So this forms a if and only if statement here. So we can say the target is easy to be approximated by the model if and only if it has low rank or we say it have low effective rank when this C1 complex measure is small, and it have small memory when this complex measure C2 is small. Okay, and next I will show some numerical illustrations of this idea. Okay, so for this thing here, we train the models with different number of layers and different number of channels to different constructed targets. So we can compute the complexity measures here. So on the left figure, we are fixed the number of layers, and we are changing the number of channels here. And on the right hand side one, we fix the number of channels, and we are changing the number of layers here. So for this one, the dotted gray line is GM. So this is we can consider this one as the error bound. So we can say it's 1 times GM is our error bound here. So all the lines below it have complexity measures less than 1, and all the lines above it have complexity measures larger than 1. So this shows that the error bound here is actually tight, and the same for the right-hand side one. And what if the error bound here is not tight? Then we will have something like this one. So for all the different complexity measures, we'll have the error bound all the way above the true errors here. Okay. So finally, I want to talk about why we want to consider the approximation of the approximation theory here. So actually, we done the approximation theory for different architectures, including RNN, encoder, decoder, CNN, and transformers. So we do the whole series of this works in the same framework. So we have different complexity measures and the approximation rates for all the architectures here. So this enables us to compare between each 6 modern architectures, and we can know how they differ from each other in the perspective of approximation theory. Okay.
Let's thank Hotya. Questions? Probably I will ask one, a general one. So I don't know much about how one could set up the approximation problem for autoencoder or encoder-decoder.
Yes.
So what are the technical difficulties that you encounter when you're trying to follow the same framework for encoder-decoders or for transformers? Could you briefly comment on that?
Yes. So for the CNN ones, we are actually considering the discrete case. And for the encoder-decoder and RN here, we need to consider continuous case because it is related with some smoothness and smoothness properties. And also for the encoder-decoder thing here, because for the RNN, usually we have the input and output have the same length here, and for the encoder decoder, the input and output may have different lengths. So the domain of the sequence, and also the definition of and to specify a good enough target, and the complexity measure is the main challenge of this one here. And also for the transformer, because it's also a very complex architecture here, and the main challenge here is to consider a meaningful form of the hypothesis space and target space. And the most important one for all these architectures is to find meaningful complexity measures to measure the complexity of the model and target, so that the results and the experiments can coincide and can have some implications on the real applications there.
So in terms of complexity measures, you're using something like Remy was doing in terms of Rademacher complexity, or you're following the same definitions of complexity measures that you were introducing in the beginning of your talk?
Yes, for our complexity measures is more like in the approximation theory. So we are considering the properties of the target, for example, like the rank, the smoothness, and something like that, and the decay of the target. It's more related with the approximation. More related with the approximation perspective.
Okay, thank you. Let's thank again the speaker.